All right, we're going to start this semester with section 6.1, which is the set of rational numbers. And the first thing I want to do is to talk about what a rational number is. So a rational number is any number of the form a over b, where a and b are integers. Now we talked about integers in Math 1, so those of you who had that class already know what that meant. But for those of you who maybe haven't, or maybe if it's been a little while, what are integers? Whole numbers, they include the whole numbers. So the whole numbers are ones we start with counting with, right? So 1, 2, 3, 4, and so forth. Integers include a little bit more than that. What else? They include 0, which is actually a whole number, so that's what Abby mentioned. What else?
It even includes the negatives.
That's the other one. It includes the negatives of those whole numbers too. So rational numbers in this form a over b have to be able to be changed to look like, if they don't already, a whole number over a whole number, and there may be a negative involved somewhere. Okay? There is one restriction. What would be the restriction that you cannot have happen?
B cannot equal 0.
That's right. Why can b not equal 0? If we had a 0, in this way we've set this up, the 0 would be in the denominator in that case, and it would be undefined. There's not any division by 0, and we'll talk more about that part later, but that is the condition. Now the fraction part right here where it says any number of the form a over b, b does not equal 0, that's what a fraction is. What's the difference between what you're seeing in where it says rational number and what we're seeing where it says fraction? They didn't have to be integers. So you have seen fractions before that don't have integers. Can you think of any place where you might have seen those or what they would have looked like? That's a very good example. If you've ever seen square roots involved where you can't take the clean out, like take the square root out cleanly, like square root of 3, that would be an example. Square root of 3 over 4, let's say, would be an example of a fraction, but it's not a rational number because square root of 3 isn't an integer and it can't be changed into an integer form. You may also have seen it if you've taken any classes with trig or geometry where you have pi's involved. If you had a pi over 4, also not going to be a rational number, but it is a fraction. Okay, so there's that small distinction. So rational numbers are fractions, but not all fractions are rational numbers. Okay. In this case, the numerator, what is the numerator of these fractions? It's a, and the denominator is b. So we call the number on top the numerator, the number on bottom we call the denominator. All right, there's several uses of rational numbers. So the first use of a rational number is that we can solve equations like 2x equals 1. If we were to solve that, what would x equal? X would equal 1/2. So you see, if we only had whole numbers, there isn't a whole number that we could put in place of x that would make this equation work, right? If you put in x equal to 0, you get 0 equals 1. Well, that's not true. If you put in x equals to 1, you get 2 equals 1, and that's not true either. So the answer has to be somewhere between 0 and 1, and there's no whole numbers between there. So that's why fractions are helpful for solving equations. Okay. The second example is a partition. So I'm going to give you an example of what a partition could look like. We could talk about 1/4 of my pay goes to rent. It is a part of something else. Right, so 1/4 would indicate being 1/4 of your pay. It's a part of your pay, a partition or a portion of. Another place you see rational numbers used is in a ratio, which should sound sort of obvious, right? We've taken rational and we've cut the word into the smaller part at the beginning, ratio. And so an example of a ratio would be something like this. The student to teacher ratio is, well, if everybody were in this class right now, it would actually be 21:1. Okay? And when we write that ratio as a fraction form, we would actually write it as 21/1. We recognize that can actually be simplified into a whole number, but 21/1 is also a fraction form of that number. Last one as an example would be probability. So when you roll a die. You have a 1/6 chance or likelihood or probability of rolling a 4. There's a 6-sided die and there's 6 numbers on there and you're choosing one of the 6. All right, so you've got some blank spots in the next slide. It says for each of the following, and there's nothing on the following, I'm going to draw them. We're going to write a fraction to represent the shaded portion. So we're going to start with a picture. So here's my first picture. So imagine that it's filled in all properly and everything. And here's my first portion of my picture. The question is, how much of this picture is shaded in? 1/6. Well, now why is it 1/6?
Because if you split the bottom section to the same equal 3 parts.
Okay,
That's really good, Hannah. Leah, Hannah was talking. Please don't talk over her. So Hannah was saying, she had a really good piece of what she said that we need to highlight, and that's the idea of there being equal portions, right? So right now the boxes as they're drawn are not equal in size. Agreed? So in order to actually compare these things, we have to talk about them being equal in size. So if we were to take this picture and sort of make all of the spaces that we have equal, it would look something like this. Then I have 6 equal portions and one of them shaded in, so that's 1 out of 6. That's a really common mistake, and your students will encounter this, is they'll look at that picture and what do you think they might say? They're going to say 1/4, because it looks like 4 portions and they've got one shaded in. So that idea of them being equal in size, it matters. This is another example very similar to that causes students a lot of trouble. So the correct answer is 1/4. And what might your students want to tell you the answer is? 1/5. Because there are 5 boxes, but not all the boxes are the same size. So if we restructured this so that the boxes were all actually the same size, we'd have 4 boxes that looked something like this, right? And then we'd have the value of being 1/4 instead of 1/5. All right, the third one. Believe it or not, they're not all rectangles when we draw these. So just to show you, we'll do a circle in. All right, so we've got a circle shape now, and I have shaded in this portion. There are 2 right answers. What's one of them? 2/6. What's another answer? 1/3. Are they equal? Yep, those are equal values. I know you guys know lots of ways to think about that, but let me think about it from a picture point of view, because that's all this really is right now is a picture. You've got 6 equal pieces, and 2 of the 6 are shaded in, so there's your 2 out of 6. Now, without doing any sort of arithmetic, which is probably what you were thinking, you can do this from the perspective of a picture too. So we can talk about 3 pieces that are equal in size. Do you see those 3 pieces that I highlighted in green, so to speak? So you've got this one piece that's in green that's shaded in red. You've got these other 2 equal pieces, so there's 1 out of the 3 pieces shaded in. And that's a much more intuitive description of why we're able to reduce 2 out of 6 to 1 out of 3. And there's no numerical messing around involved, right? It's all based on the picture. All right, one more. All right. So we've got this picture with a bunch of separate things now, right? They're not attached to each other like the rest of them. And in this picture, we're going to have this image going on. Pretend they're all shaded in properly, okay? How much of this picture is shaded in? Can you tell? 7 out of 12. And this picture looks different because it's not portions of things. But we often use this picture as a description of fractions too. So everyone in this class is female, but you would use this kind of a description if you were talking about how many of your class were female versus the whole class. Right? So imagine that each one of these small circles represented a person, and all the red ones were the females. Then 7 out of 12 kids in the class were female. And we would talk about a fraction in that way. All right. A couple of historical notes that I want to make you aware of is that as much as you may not like them, fractions have been around for a really long time. And the fractions that we work with now are much easier in some sense than some of the ones that have been worked with in the past. So the first one I want to talk to you about was the Egyptians. The Egyptians used fractions, but their fractions only had numerators of 1. So instead of writing something like 7 over 12, like the answer we just got, they wouldn't have done that. They would have talked about the number 7 over 12 as the number 1/4 plus 1/3. Not real fond of that. I don't want to be restricted to having a numerator of only 1. But that's the way that they worked with fractions. The Greeks adopted fractions with denominators of 60 from the Babylonians, and they still use that with measurement of angles. What else do we use with base 60s involved? Minutes. We use it with time. So that's another place where we see this idea of a 60 as a denominator. If you were talking about a portion of an hour, right, you've got 1 out of 60, that would be 1 minute of an hour, that kind of an idea. And then our system, it was actually developed fully when we got the modern bar that we use between these, whether you use it slanted or you use it horizontally. That bar between the numerator and the denominator came into use in Europe in the 1500s. Now, there are 3 different models that we're going to use with fractions. There's an area model, a number line model, and a set model. You've actually seen me already do an area model example and a set model example. The number line model example I haven't done yet, but let's go through them in order. The area model can be that circle picture or that rectangle picture that we just did on the previous slide over there. So an area model could look like this rectangle, and we can split it into equal pieces, and we can shade them in. And so if we look at this, this would be an area picture example of the fraction. Thank you, 3/4. All right. We're going to use that same fraction 3/4, and we're going to do the example of the other 2 as well. So if we looked at the number line example, we could actually take this and we could start at 0. And we can end at the number 1. 3/4 is actually really nice because I can cut something in half and then I can cut those halves in half. So we can talk about this being sort of partitioned. We talked about that before, this partitioning of something into pieces. And this partition, this third one would be 3/4 because there are 4 partitions, and this is the location where the third one ends. So this is my first, second, this is the third portion of this number line segment. So 3/4 is where we end this portioning. And the denominator tells you how many pieces you're cutting it into, portions of 4. Your set model is very interesting, and it has some limitations. First, let me show you what it would look like with the 3/4. And then I'll tell you why there's some limitations and what I mean by that. So you have this use of chips. And so in this use of chips, they're all the same size, just, like the ones that I did before. And I have 4 of them because I'm doing a fraction of 3/4, so there's 4 items. And I would shade in 3 of them, right? And that works just fine. But what happens if instead of having 4 chips, I actually started out with 7 chips? And I was told to find 3/4 of the 7 chips. That's inconvenient at best, right? Give me 8 chips and I'm happy. 7 chips, I'm not so happy. How do I take 7 chips and talk about 3/4 of that? Well, it doesn't work out very cleanly. So there's these limitations with this set model idea, right? I mean, I can take a whole big rectangle and split it into 7 regions just fine. That's no problem. But I don't need that for 3/4. But if I start out with 7 chips and I'm supposed to be finding 3/4, that's more complicated. So the set model has some limitations to it. All right, so the first theorem that we're going to see is something that you've seen before. You know this to be true. If you have a fraction a over b, and you have a number n that is not 0, it's actually an integer because we're working with rational numbers, then it is perfectly acceptable to use that n and multiply on the top and the bottom, the fraction of the fraction, and the fraction will stay the same value. And in many respects, we already saw one of these on the very first picture slide that we were working with. We saw a fraction of 1/3 and a fraction of 2/6. And if you think about those fractions in this sense, what's happened is that it's actually been, each of them rather, have been multiplied by the number what? 2. Right? So if I took 1/3 and I multiplied it by 2/2, I get the fraction of 2/6, which we've already looked at from a picture point of view of why that's equal. Right? Okay. But we can actually talk about it in the reverse way as well. We can talk about a rational number being in simplest form if the numerator and the denominator have no factors in common. So the reason that you've used this most commonly is to take the number 2/6 and reduce it, right? And what you do is you look and you say 2 and 6, do they have anything in common? And the answer is that they do. The answer that they haven't, the value they have in common is the number 2. So instead of actually doing the multiplication, you can do division. And if you divide them both, this is 1/3 then. The other thing to realize is that while you may have thought to yourself, hey, I'm going to divide the numerator and the denominator by 2, you really just did another form of Theorem 6.1. What you did is you actually multiplied by something. Division by 2 is the same as multiplying by what? Do you remember? 1/2. So if you think about it, if you multiplied by 1/2 on top and bottom, you would still get 1/3. And it would actually fit into the description of Theorem 6.1 with the exception of what? What is different than what that description actually says? What did we multiply by? A fraction. It didn't actually multiply by an integer. So this theorem above actually works whether it is an integer or not, okay? But it is set up to talk about it in the form of integers. So we could actually multiply the top and the bottom by a fraction, and the same result would hold true. All right, so the first thing we're going to do then on example 1 is we're going to take this fraction 3/-14, and we're going to write 3 fractions that are equal to this one. Okay? So I want you to take just a minute, jot down a couple of them. If you can come up with 3 automatically, that's fantastic. Find 3 fractions equivalent to 3/-14.
Does -3/14? Nah, it wouldn't count.
Actually, it does. We'll talk about that one in a minute, Leah.
-14.
Leah, I'd like everybody to have a chance to work, okay? And then we'll talk. Okay, so somebody give me one of the numbers, just one of the numbers you write down. All right, -6 over 28. Do you guys agree? Looks good? Okay.
How about 12 over -56?
12 over -56. What do you guys think? That'll work? Something else? 9 over -42. Does everybody agree? Now I want to come back to the question that Leah asked when I asked you guys to start working, whether or not we could actually write this one down as a separate answer. And we can. Think with me for a moment. What would I have to do to change 3 over -14 to -13? Sorry, 3 over -14 to -3 over 14.
Multiply it by 1?
Yeah. Not multiply by 1, but multiply by -1, right? So the integer n that you'd multiply would actually be multiplying the top and the bottom by -1. I know we don't think of it that way. We just think we just move the negative around. But it actually is a multiplication factor. So that's actually a legitimate answer in the mix of all of this. We were only asked for 3. We came up with 4. So we're overachievers today, right? That's right. All right, how about this one? The simplest form of 42 squared over 35 squared. So the first thing I want you to do is to answer me this question. Can I cancel out the squareds?
Oh, actually, you can.
No, I can't. That's right. I cannot cancel out the squareds. And let me give you just a concrete example as to why, okay? A small number one. Let's say that we had 2 squared over 3 squared. If we were able to simply cancel out the squareds, we'd get 2/3, right? But 2 squared is actually 4, and 3 squared is 9, and does 4/9 equal 2/3? It doesn't, because there's no number that 4 and 9 have in common to reduce it into 2/3, right? So this does not work. You cannot do a cancellation of squareds. Okay, so that said, no canceling squareds. What are we going to do with 42 squared over 35 squared?
Well, you can just...
We're going to reduce. Hannah, can you give me an example? Okay, so they both have a 7 in them. So can I write this way first? Is that all right? Sure. Okay, and so they still both have a 7. In fact, they got lots of 7s involved actually at this point now, right? So if I divide by 7 here, I'd actually divide by 7 twice. Because if I divide by 7, or you know what, one way, let me do it this way. This is what you guys are more familiar with seeing. I can reduce each one of these by a factor of 7, right? So 42 reduced by 7 would be a 6, and the 35 would be a 5. And the 42 again would be another 6, and the 35 would be another 5. How about 6s and 5s? Do they have anything in common? No. So we're done reducing, but what's our answer? Right, 36 over 25. Notice a couple of things. Number one, I don't have to look at 36 and 25 and ask myself, do they have anything in common? Why not? Because the 6 and the 5 didn't. So there's no way for that to be done.
I have a question. Could you just like break it up at first and say just 6 times 7 and put the 6 and squared over
Yes.
5 and then just cancel the 7s?
Yes, you could. I'll write that one down here in just a second. That's a good example too of how to think about it. There's one other thing I want you to notice about this answer. Some of you are looking at this answer and saying there's something wrong with it. What makes you uncomfortable about this answer for some of you? What's that? They look both square. That's a little bit weird. There's something else too. Yeah, for some reason, we don't like to have a numerator bigger than a denominator. We sort of have this sense in our spirits that that's not okay, and it is. It's just fine. So we don't need to change this into a mixed number. If it starts out as an improper fraction, it can end as an improper fraction, and that's perfectly fine. Now let me show you what Kristen's suggestion was, because it's another good way to think about this. Instead of doing it the way that I had shown it first, what we could do is recognize that 42 is 7 times 6, and that is squared. And then the denominator is 7 times 5, and that's squared. Now the reality is that that squared has to apply to each of the numbers inside, so I really have 7 squared times 6 squared over 7 squared times 5 squared, and then I could reduce the 7 squareds here. And I'm going to get the same answer. It's just a different way to think about it. Right? So we still end up with 36 over 25. All right, any questions on that one? Okay. Let's take a look at another example. Theorem 6.2 says that two fractions a over b and c over d are equal if and only if AD equals BC. So as you're taking a look at these fractions, the only way that they're equal, that is if a over b is equal to c over d, is if you're able to cross multiply them and end up with the same result. That's where that AD and that BC are sort of visually coming from. So there are actually several ways to decide if fractions are equal. This is simply one of them. All right? So we're going to determine in example 2 if the two fractions are equal. There are at least 4 ways to make that determination. Okay, so I'm going to do the one that I just told you in Theorem 6.2 first, although I don't think it's the easiest way to do this problem. And we'll talk about another couple of ways to do that after this example. So one way to check this out is to see that if I took the negative 3 over 12 and the negative 36 over 144, and we just need to decide which part we want to be negative. Or flat out, we could ignore the negatives, to be honest. They're both negative, so that part matches, right? I mean, we don't need to really even worry about that. So how about I just erase that part? There's no negatives. So we're going to do this sort of cross multiplication check step. So what happens, grab your calculator if you have it with you, multiply out for me. What is 3 times 144? $442. 442? 32? Okay. Somebody else check for me what is 36 times 12. It's 432. So according then to Theorem 6.2 or 6-2, they're equal, right? So this works out. We've checked it, so the original fractions were in fact equal. All right, so think of another way to do this. Let's say you didn't have a calculator with you and those numbers were more than you really wanted to deal with today. How else could you decide if the fractions are equal? Again, we can ignore the negative part of them. That doesn't really affect anything. You could reduce. So we can take the 3 over 12. Again, I'm ignoring the negatives because they match already. So if I looked at 3 over 12 and I reduced it, what would it reduce to? Or how would it reduce? Let's say it that way first. It would reduce to 1/4 because why? Right, you could divide the top and the bottom by 3. That's kind of nice. The 36 over the 144, you may or may not recognize readily that the 144 completely is divisible by 36. So you may not think, hey, I'll try to divide the top and the bottom by 36. Right, you might not think that. But you might notice, hey, those are both multiples of 12. That's one of the multiplication sets they teach children right in 3rd grade-ish. And we could start there. So what's 36 divided by 12? 3. And 144 divided by 12? 12. And we've already said that that's 1/4, right? So they both reduce to the same thing. That's a second way to do this. So we can reduce the fractions. That's an option. What's another way we could do this?
Would you like multiply
Very good. So I've got 3 over 12, and you might look at this and recognize, as you're comparing them, hey, this one has a denominator of 12, and that one has a denominator of 144. So what I could do is I could get them to have the same denominator. And if they had the same denominator, then I could compare them by simply comparing the numerators, right? I mean, the reason we know that 1/4 is smaller than 2/4 is because the denominators match and the numerators are different. So we could get the denominators to match. There's 2 ways to get the denominators to match. On this one, it's very obvious to know what to multiply by so that you only have to multiply one fraction, right? You need to multiply the first fraction by the number 12. Now that doesn't always happen. It's not always so obvious what to do. So if we do this, we can change this then pretty quickly into 36 over 144 and recognize, hey, we got the same denominator, we have the same numerator, they're the same fraction. Okay? What if we didn't recognize so readily the number that we needed to multiply by? What if instead of it saying 12 and 144, it said 11 and 144, 13 and 144, 14 and 144, which would be actually the worst because you know they're even, but they don't seem to be multiples of each other. So a third option, this is what we just did in the last example, was the least common denominator. The last option of how to do this is to use what's called a common denominator. So the way that you do a common denominator is you simply multiply the denominators by each other. It's not terribly efficient in this example, but it works. So we can take 3 over 12 and 36 over 144, and we can multiply the first one by 12 over 12, and we can multiply the second one, I'm sorry, I said the wrong thing. The first one by 144 over 144, and the second one by 12 over 12. You're just multiplying by the denominator that's not there. All right, so somebody's going to give me some values. What's 3 times 144? What is it?
I said a large number.
It is a large number, I agree. Do you have it, Lydia?
432
Are you doing the 12, 144 now?
over 1,720.
Okay. And the second one, of course, works out to being the same thing, right? And that's actually, it seems silly on this one, I know. But if you'd had 14 and 144, it'd be easier to do that than to find the least common denominator. It just would. Especially if you've got a calculator to do the multiplication for you, right? Yeah. All right, so that's a third option, or fourth option of how you can actually compare whether fractions are equal or not.
I have a question.
Sure.
If we're like reducing in our homework, do you want us to actually, like the 36 over 144, do you want us to write out divide by 12? Or do you like...
No, you don't have to. You do not have to do that. But you do need, I mean, if you do multiple steps, show me the multiple steps of your division. Yeah. Yes.
Did you say when we were starting that the A wasn't the easiest one, like just cross, like?
It isn't always the easiest one, because sometimes it results in really large numbers.
Okay.
Sometimes it's easier to reduce things than to do anything else.
Okay.
It just depends on the situation. Yeah. All right, a couple more theorems for us. Theorem 6.3 or 6-3. We have integers a, b, c, and I actually alluded to this earlier, and we want to compare a over b and c over b. Notice the b and the denominators are the same. Then the way that the first fraction is larger than the second one is if and only if the first numerator is larger than the second one, right? Why is 1/4 less than 3/4? Because 1's less than 3. Okay, they've got the same denominator. We don't have to compare anything with the tops, right? Now, the second one here, Theorem 6.4, is not quite so clean because the numerators and the denominators are different. So if you don't have the numerators or the denominators the same, you can't just look at one piece and make that decision and always be correct. But notice that this Theorem 6.4 looks an awful lot like the last Theorem 6.2 that we did, doesn't it? What does it look like they did? They cross-multiplied, right? It looks like they took this A and this D along that diagonal and multiplied them. And then the other diagonal, B and C, and multiplied them. And notice the sign stays the same direction. which is awfully nice to remember, right? So this is another way of comparing fractions. So example, on the last one, if instead we found out that they weren't equal, but the first one was larger than the second one, when we did this cross multiplication, then that means the first fraction is larger than the second one. All right, so we're going to take an example here. This is example 3. Example 3 has 3 fractions, though, that we're comparing. We have the fraction 13 over 20, 3 over 5, and 7 over 10. Now, we could do the cross multiplication. Shana, this is like the one that you and I just were talking about, right? We could do the cross multiplication, but the cross multiplication only works if you're putting 2 numbers in order, right? I've got 3 numbers, and I don't want to keep doing this cross multiplication lots of times. How else could I put these in ascending order correctly? The same denominator would work really well on this one, wouldn't it? Because the denominators are similar enough that when you look at them, you say, oh, well, they're all just multiples of 5, right? I've got a 20, I've got a 10, and I've got a 5. So if we get them all to have a common denominator, that would be good. And there is a least common denominator that you probably look at this and just say automatically, what is the least common denominator between 25 and 10? 20, right? I can turn the 5 into a 20, and I can turn the 10 into a 20 pretty well. Now, if you didn't recognize that readily, or if it simply wasn't one that's like that very nicely, you could just multiply the denominators by each other and it would work too. You just end up with larger fraction values to work with, right? Yeah, okay. So the 13 over 20 is good as is. I'm not going to mess with him. What can I do to the 3 over 5 to change it into having the same denominator as the 20? All right, multiply by 4. So what is this fraction? Good, 12 over 20. All right, now we've got a 7 over 10. What do I need to multiply this one by? 2. Okay, now be careful as you say that. I know what you mean, but what you really meant to say was 2 over 2, right? Not 2. 2 over 2. All right, so what is this fraction when we multiply? 14 over 20. All right, so looking at these values, which one's the smallest? The one in the middle, right? And actually what Leah just said was really important. She said 3/5. Many of you are saying 12/20ths, and I know they're the same, but why do I want my answer to say 3/5? Because that's what the problem was given as, right? Yeah, that's how it was given to start with. What's the next largest? The 13/20ths, which is how it was given, so we'll write 13/20ths next. And then the last one is the largest, and that one should be written as 7/10. You could write those with the less than signs like I did, or you could just put commas between them because the directions just said put them in ascending order, so you didn't have to have the less than signs to show the ordering. All right, example 4. Choose less than, equal to, or greater than to correctly go between the following. Again, there's lots of ways to do this. So one way is that we could do the cross multiplication. Agreed? And that's okay, but I'm going to have some large numbers if I do that. What else could we do? We could get a common denominator, right? We could do that. So I think common denominator works really well for this one because the denominators are really similar to each other. Yes, Kinsey?
I have a question. Like,
Sure.
if you just look at it, like, you know that 21 times 200 is obviously going to be like 100 or 30.
Okay. That was the next thing I was getting to. So you're doing awesome. Yes. So Kinsey's saying she can just look at it and tell that there's a certain one that's smaller or larger than the other one. And I agree that I can too. You may or may not be in a position where you look at that and just say, well, it's obvious to me. So when I'm looking at this, I can think about this in terms of approximations and make my decision pretty quickly. This is about 20 over 400, right? I can reduce that pretty quick. This is about 50 over 200, right? Well, 50 out of 200 is a lot more than 20 out of 400. So it becomes pretty quick and easy if you don't want to do the mathematics to be able to justify that with some language, okay? So if you choose to justify it with that language, Kinsey, that'll work. Or you can choose to justify it with numerical work to show why it's working too. Right? So for those of you who want to see the numerical approach, I'm going to do that next. So what could we multiply which fraction by to make the denominators the same? Right, we can multiply the second fraction by 2 over 2. Yes. So this is 21 over 430, and this becomes 430. What does that numerator become?
102.
102, that's right, yes. And we're very quickly able to see with the numbers that that works too, right? I hope that what you're getting the sense of in this so far is there's lots of ways to do these problems. I hope that's what you're getting, because that's the case. I mean, that's what we're encountering as we're working with these, is lots of ways, and they're all correct to do the same problems. Okay. Next thing, 6.5, denseness property for rational numbers. It says, given two different rational numbers, a over b and c over d, there is a rational number between them. Okay, so a over b and c over d just represent two numbers. The easiest way to justify this or to think about this is to think about this in terms of the number line model that we talked about before. I don't know which one's smaller. It doesn't really matter, but somewhere along the number line is the a over b, and somewhere is the c over d, and we're told that they're different. So they're in different locations. So if you imagine, even if they're really, really close, think about what your calculator does. You guys have seen graphing calculators before. If you zoom in far enough, what happens to these numbers that look really, really close? They look like they spread out, don't they? And all of a sudden, somewhere in the middle, you notice there's some space there. There's a little bit of space between them. All this theorem is saying is that that little bit of space represents that there's another number that's between them. That's kind of cool. Now, the next theorem actually tells you one way to find one such number. There are other ways, but this is a really nice one. Because sometimes the numbers are really close together, right? If you have 3/7 and 4/7, it doesn't look like there's any space between them when I write the fractions out. But here's an example. So if I have this a over b and this c over d, and my a over b smaller, one way to find a number between them is to add the numerators together and to add the denominators together, and you will have a number that is between them. Well, that's pretty cool. I mean, that's a pretty nice fact to have. So if you take an example like I just said, 3 over 7 and 4 over 7. Now, it doesn't ensure that it's exactly halfway between, but that's not what we're trying for, okay? We're just looking for something in between. Well, I can add the 3 over the 7, the 3 and the 7, sorry, the 3 and the 4 together, and I can add the two 7s together, and I end up on this one getting a 7 out of 14. That happens to reduce in this case. Sometimes it won't reduce, right? This one happens to become something that I can reduce to 1/2. If it is able to be reduced to 1/2 at this point, we would reduce it. But oftentimes it won't be. Okay, so we're going to do an example of one where the numbers are even closer together. We've got 33 over 427 and 34 over 427. And let me just say real quick that there's absolutely no reason the denominators would have to be the same here. They just were in the ones I picked. Okay. So how would I find a number between these? Add the top and add each of the bottoms. Is this the only number between these? No, there's infinitely many numbers between them, actually. Lots of them. Because all this does is give me another rational number. And I can take this new rational number and one of the original rational numbers and just do it all over again. All right? So what is 33 plus 34? 67. And what's 427 plus 427? 854. And I don't think that reduces. Okay. All right, so I'm not going to write this in, but I want you to write it in. Why must there be a number between these fractions? We've already talked about this. So in your own words, write in, for example 6, why there has to be a number between these two fractions. What'd you say? Why must there be a number between the two fractions?
There's an infinite amount of points on any line or in any space. There's no way to.
I like that. There's an infinite number of points along a line segment, right? So all you've really got here is a line segment. And there's an infinite number of points between there. Sound pretty good? Did anybody write something different? Yeah.
I said, I don't know if this is right, but I said if there is no number between them, then essentially the two fractions are the same because there's nothing separating them.
That's also a very good way to describe it, right? If there weren't a number between them, they must have been the same number to start with. This idea of denseness, this idea of there being these values or there's being infinitely many points between 2 points, that sort of thing, is what's going on in this problem. Right.